Hi friends, so today we begin lecture 56 on our helicopter dynamics course, and today I'm going to look at the flap equation and specifically investigate the stability of this equation in terms of the eigenvalues in the rotating frame. I'm Dr. Ranjan Ganguly. Now we will start by making our life simpler, and so we are going to use the equation when mu is equal to 0. So you saw in our previous lectures that the forward flight equation is extremely complicated because the right hand side in terms of m beta bar becomes very complex. So what we do is we bring the motion dependent term involving beta star to the left hand side, and then we look at the stability of this equation. Now when you look at stability of a differential equation, you can set the forcing to 0 except if there are motion dependent terms such as involving beta star. Here you have to bring them to the left hand side. Okay, so now we have 4 blades, let us say. Well, we could say there are m blades in general, but we'll think about 4 because it is more material in that sense. And therefore we now look at this equation, and we clearly see that this equation is very similar to a typical spring mass damper system. So the first term would be a mass term, the second term would be a damping term, the third term is a stiffness term. And essentially you clearly see here the damping is coming from the aerodynamics because gamma is here, and remember gamma is rho a c r4 by ib. So if rho is 0, then gamma is 0. So totally depends on the presence of density of air, and therefore if you are in vacuum this term would vanish. Now to investigate the stability of this equation, we set beta m psi as beta m bar value into e to the power sr psi. Okay, so this is very similar to what we do for solving any kind of differential equation with constant coefficients, and then we plug it into the differential equation. So this is a presumed solution of the differential equation, and what happens after we plug it in is that we do the requisite differentials. So we get a SR squared term here, we get a term SR here, and this term just remains nu beta squared into a 1. So essentially now this particular characteristic equation must be equal to 0 for this system to have a non-trivial solution. And therefore this being a quadratic, I can immediately solve this in terms of SR. So SR would be negative gamma by 16 plus minus I root nu beta square minus gamma square by 16. Okay, so here we clearly see that the eigenvalues are complex conjugate pair, and therefore for each particular blade, this equation essentially holds for blade number m. We obtain a pair of such roots. So there would be n pairs for n blades, and all the pairs would have exactly the same form. Now, typically if you go back to our thinking about a spring mass damper system, you will recall that the real part of this would be damping. So this term negative gamma by 16 would represent a damping type of term, and the imaginary part represents frequency. So these are the two aspects of the system that we need to keep in mind. So now let us take a look at this equation and just examine a particular special case. So let's presume we are in vacuum. In that situation, gamma would be 0. And so SR would be plus minus I root nu beta square, which would be plus minus I nu beta. So essentially in a vacuum, you would only have frequency, you would not have any damping, and therefore the motion would just continue on and on. There is no damping to suppress that particular motion or to decimate it in time. But when you are in actual air, the density being present there, there is a Lock number present there. So let's take a typical value of log number such as 8, a typical value of nu beta such as 1 for a blade which is hinged at the root. So then we can write the equation here: 2 zeta nu beta is gamma by 8. Okay, and from this I can solve for zeta here, which is the damping ratio, and that takes this form here. I put in all the terms here. Gamma is 8, and then I have 16 here from 8 into 2, and then nu beta is 1, and from all these I get zeta is 0.5. Now if you recall our study of structural dynamics, this is a very high level of zeta. In general, zeta varies from 0 to some low number. It could be 0.05, zero point 0.1 or something like that. Zeta 0.5 is quite high. It is halfway to critical damping, in fact. And therefore we can say that the flap mode is highly damped. This is an aspect of rotor dynamics which you need to remember all the time, that the flap mode is very well damped. The damping is essentially coming from the fluid mechanics, and therefore you don't need to bother much about the stability of the flap mode. We typically are doing all this to develop the mathematical tools to find out about stability. But in general, for the flap mode, we don't need to bother about stability. Of course, remember that all this would be slightly different or considerably different if you were in a different planet where the properties of air are different. So if you are on Mars, then things would change because density of air there would be very low. So now let's look at the frequency part of this particular case we have conjured up. So if we put the same value, nu beta is 1 and gamma is 8, we get the frequency of vibration is 0.87 per rev. And recall that from this expression, this is like a damped vibration. So the frequency of vibration due to damping becomes less than 1 per rev, and that is the damped vibration frequency. So we see that damping is quite substantial because it has a substantial impact on the frequency of vibration. The frequency has come down all the way from 1 to 0.87 per rev. Now we are actually going to go further, and we are going to look at these equations once they are transformed into a non-rotating frame. Now, why do we do this? One of the reasons is that sometimes the rotor motion couples with the body motion. And in those cases, we actually have to take the rotor equations, convert it to the fixed frame, and then couple it with the equations, for example, of the fuselage or the ground-based landing gear system and so on, in cases such as ground resonance, which we will discuss later. So one of the ways to convert these equations to the non-rotating frame is to use these four equations for transformation. And here your beta m are the degrees of freedom in the rotating frame. And when you transform to the fixed frame, you get beta 0, beta nc, beta ns, and beta n by 2. Now, these degrees of freedom are in the non-rotating frame. So here your psi m in the rotating side of the equations would correspond to psi plus m into delta psi, and delta psi is 2 pi by n. So that essentially ensures that you are capturing the appropriate psi for the different locations of the n number of blades. So this particular transformation which I discussed in the previous slide is known as the Fourier coordinate transformation, and it's very important in helicopter dynamics and rotor dynamics. Essentially, this helps us describe the motion of the rotor in the non-rotating frame, which I mentioned becomes very important if you want to develop coupled equations later on. Also, we pointed out that beta superscript m is the degree of freedom in the rotating frame. And remember that FCT is a linear transformation from the rotating frame to the non-rotating frame, and the terms which we expressed in the non-rotating frame such as beta 0, beta n by 2, beta nc, beta ns are actually degrees of freedom of the system. They are different from the coefficients of the Fourier series. So though we use similar terminology, the thinking here is somewhat different. These are actually degrees of freedom. So in the next lecture, I'm going to look at the flapping equation in the non-rotating frame and see the roots of those equations, and that in fact is going to lead us to some modes, specifically the high frequency and low frequency modes and the progressive and regressive modes. See you then.